The next problem which I am going to discuss is on beams. Beams are the structural members which are subjected to transverse loading either in y direction or in z direction, not along the length of the member. There can be also loading along the length of the member, but beam is structural member which should withstand bending stresses. Now, for a beam to withstand bending stresses, its depth should be greater than its width. Okay, in the area of cross section, this is a 0.2 meter. This depth should be greater than this width. Okay. Now I am going to talk about simply supported beam. I will explain how to model the cantilever beam after discussing of the simply supported beam. It should not be difficult for you to model the cantilever beam, to analyze the cantilever beam after discussing the simply supported beam. Let us go to the problem directly. The problem first: preferences, structural, okay, preprocessor, element tape, add the element, add beam element, two nodes, node I and node J, 188, okay, options. We need to select cubic shape function, cubic form, Hermite shape function, okay, close. That you should be conscious while selecting it. Material properties, material models, structural, linear, elastic, isotropic, and the Young's modulus is 210 GPa, 210 e power 3, Poisson's ratio is 0.3, say okay, close. Section, since the beam section, beam, common section, since the dimension is given as 0.1 meter into 0.2 meter, in this problem I will try to represent everything in terms of meters only. Let's see. Then I have to change my this one in material property. Let us define as 0.1 and width, height as 0.2. Say apply. You can see the preview also. This is the Young's model, the area moment of inertia in z direction, and then area of cross section 0.1 into 0.2, 0.02 mm square. Say okay. I'll change the material properties, material models, isotropic. I'll make it to, I'll convert it into GPa in Newton per meter square, 210 e power 9 Newton per meter square. Say okay. Close. Modeling, create nodes in active coordinate system. Delete this. You should be conscious. We are doing it in terms of meter. Apply. The next node is that wherever there is discontinuity, you have to create a node. 2 meter. Apply. This is discontinuity of load, and the next node is at 4 meter. Say okay. Elements, 2 nodes, auto number 2 nodes. Say apply. Second and third. Say okay. The load is at the center of the beam. Midspan, loads, define loads, apply, structural, displacement. While defining the boundary condition in case of beams, you should be very conscious. So the boundary condition what we use here is at the node I, that is at the left hand node, it is free to rotate over to only in the z direction. The translation x and y, z and z, x, y and z direction are fixed. The rotation about x and y directions are fixed, is 0, whereas in case of node J, that is in node 3, the translation in x direction is free, rotation about z direction is free, whereas translation in y and z direction are fixed, rotation about x and y direction are 0. Okay, let me define once. If I define it, you will come to know. On nodes, select this node. Okay. Translation, 3 translations are fixed. Rotation about x, rotation about y is fixed. Say okay. Select the node. On node, say okay. Okay. Translation in x, in case if there is a generally, in case if the beam is subject to any temperature changes, it should be free. It is an assumption that the beam should be free to expand. So there is a translation degree of freedom in x direction is free. So ux is free, uy, uz, rotation x and rotation y are constrained. Say okay. Force or moment or nodes, select this node, say okay. A force of magnitude Fy, this is negative bidirection, minus 10 e power 3 is applied, say okay. Solution, solve, current row step, say okay, solution is done. In order to display the bending moment and shear force and bending moment diagram, we need to call it, go to element table, define table, add by sequence number SMISC 6, apply by sequence number SMISC 19, apply by sequence number SMISC 3, apply by sequence number SMISC 16. Okay, you should note that for bending shear force diagram it is SMISC 6 and 19, for bending moment diagram it is SMISC 3 and 16. You should remember that. Close. I will call that plot results, line elements results, SMISC 3 and 16 for BMD, 3 node I, 16 for node J. Okay, this is the bending moment diagram, isn't it? W is equal to PL by 4. The maximum bending moment will be that P by 2 into L by 2. This is the maximum bending moment occurring at the mid span. Okay, line element results. Let us see the shear force diagram. Okay, this is the shear force diagram. Also, we can see the stresses in x direction. Since in a beam, stresses are induced in the x direction, we can go to list results, element solution, x component of stress. This is the stress in x direction. Node 1, node 2, we can see it is calculated. Okay. You see the stresses in x direction, start controls, style, size and shape. Switch on this. Say OK. Plot results, contour plot, element solution, stress, x component of stress. Say OK. These are the stresses in x direction. This maximum is 30 MPa. 30 MPa is the maximum stress induced. There is a dispan. Okay. This is about the simply supported beam. After understanding the simply supported beam, it should not be difficult for you to solve the problem on cantilever beam. Everything remains the same. Everything remains the same. The only thing what you have to do in case of cantilever beam is the left hand support has to be completely constrained. Ux, uy, uz, rotation about x, y and z should be completely constrained, and then a point load at the tip has to be applied at the right end. Okay, that's the only difference between cantilever and simply supported beam. The boundary condition obviously it varies, but it is cantilever is very easy to analyze. The left hand support has to be completely constrained, and the right hand tip a point load has to be applied. We know that the bending moment, the shear force is given by, in case of cantilever, P into L. Sorry, bending moment is given by P into L. It will be a triangle like this, varying downwards. So that is the maximum bending moment occurring at this point.